We are in chapter 4 where we are discussing bending. This is the 23rd session overall, and here we look at examples using the relationship between UDL, SF and BM. This is a glimpse of the sessions covered in the first 4 chapters. We are in session 23. In the last session, we discussed a relationship between UDL, BM and SF. Here we look at examples based on the relations. After this, we look at singularity functions. We have earlier discussed the relationship between UDL, SF and BM. We mentioned that these relations would be helpful for developing shear force and bending moment diagrams. We have earlier seen how they are helpful for problems that are algebraic in nature. Here we will see that they are helpful for other types of problems as well. The procedure used here is different from the methods we have used till now. The procedure is based on the relationship between UDL, SF and BM. It is based on summation. Let us consider this problem. This case has overhang on both sides. The overhang on the right is more than the overhang on the left. The total load is 6 into 18, that is 108 kilonewton. The resultant acts at 9 meters from E or 5 meters from B. We initially get the reactions at A and B. To start with, we take moments about B. Then Ra into 12 is equal to 108 into 5, from which we get Ra is 45 kilonewton. Summing of forces in the vertical direction, we get Rp as 63 kilonewton. In order to find the shear force diagram, we will repeatedly use this relation. Here we have 6 into 2 between D and A as the area of the load diagram. So the area of the load diagram between D and A is 12. Then using this formula, we can write VAD is equal to VA minus VT is equal to minus 12. Now here VT is 0. Then we get VA as minus 12. So we have plotted VA as minus 12. The distributed load is constant. So we have joined the shear force at A and D by a straight line. At A reaction 45 kilonewton acts. So just to the left of A, the shear force is minus 12. And to the right of A, the shear force is minus 12 plus 45, that is 33 kilonewton, which is shown here. Now the area of the load diagram between A and B is 6 into 12, that is 72 kilonewton. Again, using this formula, we have VBA is equal to VP minus VA equal to minus 72. Now VA is 33, from which we get VB as minus 39 kilonewton, which we have plotted here. Between A and B, the loading is UDL, so the shear force at A and B has been joined by a straight line. Now at B, force of 63 kilonewton acts. So just to the left of B, the shear force is minus 39, and to the right of B, the shear force is 24 kilonewton, which we have plotted here. Between B and E, the area of the load diagram is 6 into 4, that is 24 kilonewton. Again, using this formula, we get VEP is equal to VE minus VP equal to minus 24. Now VP we have found out to be 24, which gives us VE is equal to 0. As usual, we have joined the shear force at B to the shear force at E by a straight line. We can find AC by considering proportions. So 33 divided by AC is equal to 39 divided by CB, from which we get AC as 5.5 meter and CB as 6.5 meter. Here we develop the bending moment diagram for the problem we are considering. For developing the bending moment diagram, we'll be constantly using this formula. The manner in which we develop the shear force diagram from the load diagram, in the same manner we'll develop the bending moment diagram from the shear force diagram. Bending moment diagram will be developed in tandem with the shear force diagram and will constantly use the shear force diagram and this equation. To start with, we find the area of this triangle between B and A. So it is given as 12 into 2 divided by 2, and it is negative, so it is given as minus 12 kilonewton meter. Using this formula, we get MAD is equal to MA minus MD is equal to minus 12. Now MD here is 0. So we get MA is equal to minus 12 kilonewton meter. So we have plotted MA as minus 12 kilonewton meter. Give the bending moment variation between D and A, we notice three things. The variation here of the shear force diagram between D and A is linear. So the variation between D and A of the bending moment diagram would be quadratic. In the shear force diagram, we are in the negative region. So the slope of the bending moment curve would be negative. The ordinate of the shear force diagram varies from 0 to a larger value, and as such, the slope of the bending moment diagram will vary from 0 to a larger value. Next, we find the area between A and C of the shear force diagram, which is given as 33 into 5.5 divided by 2. That is 90.75 kilonewton meter. Again, using this equation, we have MCA is equal to MC minus MA is equal to 90.75. We know MA, so we get MC as 78.75 kilonewton meter, which we have plotted here. The variation of shear force between A and C is linear, so the variation of the bending moment diagram will be quadratic. We are in the positive region in the shear force diagram, so the slope in the bending moment diagram will be positive. We move from a higher value of shear force to 0. So here the slope changes from a higher value to 0. Now between C and B, the area in the shear force diagram is 39 into 6.5 divided by 2. That is minus 126.75 kilonewton meter. Hence again using this equation, we get MBC is equal to MB minus MC is equal to minus 126.75. Now we already know MC, so we get MB as minus 48 kilonewton meter. So we have plotted MC here. The variation of shear force between C and B is linear, so the variation of bending moment between C and B is quadratic. In the shear force diagram, we are in the negative region, so the slope between C and B would be negative. The ordinate of the shear force moves from 0 to a higher value. So here the slope of the bending moment moves from 0 to a higher value. Area between B and E of the shear force diagram is 24 into 4 divided by 2, that is 48 kilonewton meter. We again use this equation. MEB is equal to ME minus MB is equal to 48. Now MB is minus 48. So we substitute that and we get ME is equal to 0. Between B and E, the shear force is linear, or the bending moment is quadratic. Between B and E, we are in the positive region here. So the slope, the bending moment diagram will be positive, and we move from a higher ordinate in shear force to 0. So here we move from a higher slope to 0 slope. So now we have the whole bending moment diagram. Here we have another problem, and we'll find the shear force and the bending moment diagram for this case. To start with, we find the reaction RA. So we take moment about point B, RA into 5 minus 12 into 8 minus 10 into 7 is equal to 15 into 5 into 2.5, from which we get RA as 70.7 kilonewton. Now the total load acting is 22 plus 75, and from which we get RB is 26.3 kilonewton. Unlike the previous problem, here we will use this relation only partially to draw the shear force diagram. At C, there's a 12 kilonewton force acting, so the shear force is 12 kilonewton. At E, we have another 10 kilonewton acting, so the total shear force becomes 22 kilonewton. And it does not change till we reach A. To the left of A, the shear force is minus 22, and there's a force 70.7 acting at A. So the shear force rises to 48.7 just to the right of A. Between A and B, the total area of the load diagram is 15 into 5, which is 75. We now use this equation. So VBA is equal to VB minus VA is equal to minus 75. We have found out that VA is 48.7. So we get VB as minus 26.3 kilonewton, which we have plotted here. Between A and B, the distributed load is constant, so the shear force variation would be linear. The reaction RP acts at B, so the shear force at B reduces to 0. We can find the point D between AB where the shear force is 0. So 48.7 divided by AD is 26.3 divided by 5 minus AD, which is dB. We get AD is equal to 3.246 meter. Here we develop the bending moment diagram. Earlier, when determining the shear force diagram, we used the integration formula for only A to B. We did not use the integration formula for the whole beam. However, when developing the bending moment diagram from the shear force diagram, we will be using this formula for the whole beam. We'll be developing the bending moment diagram in tandem with the shear force diagram. We'll constantly refer to the shear force diagram and this equation. Between C and E, the area of the shear force diagram is minus 12. So we have plotted the bending moment at E as minus 12. Since this variation is constant, the variation in the bending moment diagram is linear. The area between E and A here is 22 into 2, and it is negative. So the area is minus 44 kilonewton meter. This gives the total area of this portion as minus 56 kilonewton meter. We now use this formula. Now MAC is equal to MA minus MC is equal to minus 56. MC is 0, so which gives us MA is equal to minus 56. So we have plotted the bending moment at A as minus 56. This variation is constant, so the variation between E and A is linear. The area between A and D in the shear force diagram is 48.7 into 3.25 divided by 2, that is 79.06. We again use this equation. MdA is MD minus MA is 79.06. MA is minus 56, from which we get MD is 23.06 kilonewton meter. So here we have plotted MD. Since this variation is linear, this variation is quadratic. Here we are in the positive region, so the slope is positive. Here we move from a higher shear force value to 0. So here we move from a higher slope to 0 slope at B. Between D and B, the area is 26.3 into 1.75 divided by 2, that is minus 23.06. We again use this equation, so MBD is MB minus MD is equal to minus 23.06. Now MD is 23.06, which gives us MB is equal to 0. So here we have developed the whole bending moment diagram. Here we have a overhanging beam with the overhang on the left side and a distributed load and a moment acting on it. For this problem, we can develop the shear force diagram from the loading diagram using the integration method on the full. However, because there's a moment acting, we cannot develop the bending moment diagram from the shear force diagram wholly. To start with, here we find the reaction at A. We take moment about B. Then RA into 6 plus 25 is equal to 9 into 6 into 5, from which we get Ra is equal to 40.83 kilonewton. This whole load is 54 kilonewton, and summing up forces in the vertical direction, we get Rp is 13.17 kilonewton. We'll now use this equation and the load diagram to develop the shear force diagram. Between C and A, the area of the load diagram is 18. Then we get VAC is equal to VE minus VC is equal to minus 18. Now VC is 0, so we get VA is equal to minus 18. So here we have plotted VA. The shear force at C is 0 and the loading here is constant. So we join these 2 points by a straight line. Just to the left of A, the shear force is minus 18. At A, there's a force of 40.83 kilonewton acting. So the shear force just to the right of A rises to 22.83 kilonewton. Between A and E, the area of the loading diagram is 9 into 4, that is 36. Then VEA is equal to VE minus VA is equal to minus 36. Now, we earlier got VA as 22.83, which gives us VE as minus 13.17 kilonewton. Here we have plotted VE. The loading variation is constant, so the shear force variation would be linear, and we have joined the shear force at A and E by a straight line. RP is 13.17, so we get VP is equal to 0. We can find out where F is, so 22.83 divided by AF is equal to 13.17 and divided by FE, from which we get AF is 2.536 meter. Here we plot the bending moment diagram. As earlier mentioned, the bending moment diagram will only be partially formed from the shear force diagram, since there's a moment happening in the load diagram. So at D in the bending moment diagram, there's a 25 kilonewton meter moment. This moment stays the same till C. After C, we use the shear force diagram. So the area between C and A is minus 18. Using this formula, we get MAC is equal to MA minus MC is equal to minus 18. Now MC is 25, so we get MA is equal to 7 kilonewton meter. This variation in the shear force diagram is linear with the ordinate rising as we move from C to A. So this is the bending moment diagram we get, but the curve is quadratic. Between A and F, the area is given by 22.83 into 2.536 divided by 2. So this is the area. Now MFA is equal to MF minus MA is equal to 28.95. Now MA is 7, from which we get MF is 35.96 kilonewton meter. At F, the shear force is 0, so we have the highest bending moment. This variation is linear, so the corresponding variation in the bending moment diagram is quadratic. The area between F and E of this triangle is given here. MEF is ME minus MF is equal to minus 9.64. We know MF and we can find out MB, which we get as 26.32 kilonewton meter. Again, the variation between F and E of the bending moment diagram is quadratic. Between E and E, the area of the shear force diagram is this value into 2, so which we see here. Hence, MBE is MB minus ME is minus 26.32. Now ME is minus 26.32. So MB is 0. We have given the whole bending moment diagram.